Hey everyone, and welcome to today's Explainer. I am so thrilled you're here. We're actually going to just totally skip the usual agenda today because I want to jump straight into a story that is quite literally powering your life right at this very second. We're going to unravel the hidden engineering behind modern electronics. And I promise you, once you understand this invisible world that's operating right under your fingertips, you are never going to look at your screens the same way again. So think about this for a second. If I asked you, what's the single most important invention of the last 100 years, what would you say? The internet? Spaceflight? Maybe the automobile? It's a massive question, right? But the really surprising answer, it isn't a towering rocket or some sprawling global network. It's actually something so completely invisible you've likely never even laid eyes on one. The answer is the transistor. And the sheer scale of this invention is just staggering. Right now, literally as you're watching this, there are billions of these tiny, invisible little inventions working together inside your phone or your computer. Billions of them. And they aren't just sitting there, They're flipping on and off millions or even billions of times every single second. Without them, there are no smartphones, no internet, and absolutely zero modern computing. Okay, let's dive right into this. To truly appreciate why the transistor was such an incredible leap forward, we kind of have to look back at what engineers were forced to deal with before it existed. So early electronics relied on things called vacuum tubes. Picture these glass bulbs, incredibly similar to small light bulbs, right? They controlled the flow of electricity by heating a filament inside a sealed chamber. Now, they did make early radio and computing possible, but man, they were a total nightmare to manage. They were bulky, they generated intense heat, sucked up massive amounts of power, and worst of all, they were terribly fragile. Just like an old light bulb, they were constantly burning out. Engineers knew they desperately needed an alternative. They needed something solid, sturdy, and made from a material known as a semiconductor. To paint a vivid picture of just how paralyzing this vacuum tube problem really was, let's look at the ENIAC. Completed back in 1945, this was an early electronic computer, and it was an absolute beast. It used over 17,000 vacuum tubes. It filled an entire massive room. And because those glass tubes generated so much intense heat and just kept burning out, the ENIAC actually required a fully dedicated maintenance team. Their entire job was basically just running around swapping out broken glass bulbs just to keep the machine thinking. If human progress was ever going to advance beyond machines the size of a gymnasium, well, something had to change. That desperate search for a better way led scientists at Bell Labs to really start investigating semiconductors. Now, what's super fascinating here is the actual nature of a semiconductor itself. Think about a standard conductor, like a copper wire. Electricity flows through it totally freely. Then think about an insulator, like rubber or glass, which blocks electricity completely. A semiconductor, utilizing materials like silicon or germanium, sits right in this strange, unique middle ground. What made them so fascinating to researchers was that under the right conditions, you could actually control and adjust their ability to conduct electricity. They could potentially do the exact same job as a giant, incredibly hot glass vacuum tube, but in a tiny, solid, perfectly reliable package. And that brings us to a chilly Tuesday in late 1947 at Bell Labs. You've got a team of 3 physicists, John Bardeen, Walter Brattain, and William Shockley, and they were deep into months of super frustrating trial and error. But then, on December 16th, their persistence finally paid off. Bardeen and Brattain successfully built the very first working transistor. It was hand-built using just a small germanium crystal with 2 thin gold contacts pressed incredibly closely together on its surface. When they applied a tiny electrical signal to one contact, it amplified a much larger signal flowing through the crystal. No massive heat, no fragile glass, no burning out. Interestingly enough, their supervisor, William Shockley, kind of felt left out of that specific breakthrough moment, so he channels his frustration into designing a sturdier, way easier to manufacture version called the junction transistor. Ultimately, all 3 men shared the 1956 Nobel Prize in Physics for a device that, honestly, almost no one outside their lab really understood yet. So how does this tiny, Nobel-winning piece of germanium actually work? Well, let's break it down mechanically using a really simple analogy, a water valve. A transistor basically has 3 connection points: the base, the collector, and the emitter. Picture the collector and emitter as a wide water pipe, and the base is a hand turning the valve on that pipe. A tiny, weak electrical signal applied to the base acts exactly like that hand turning the valve. It opens the gate, allowing a massive electrical current to flow freely through the pipe between the collector and the emitter. And if there's no signal to the base, the valve shuts perfectly tight. So the really crucial takeaway here is how this simple physical valve behavior creates the entire foundation of our digital world. When no signal is applied, the valve is closed, current doesn't pass, and we call that state 0. When a signal is applied, the valve opens, current flows freely, and we call that state 1. This exact binary behavior, on or off, 1 or 0, is literally the fundamental language of all digital electronics. But the true power here isn't just in representing a 1 or a 0. It's all about the speed. Because these solid-state switches don't have to rely on heating up a physical filament inside a fragile glass tube. They can flip between these two states incredibly quickly. I mean, we are talking millions or even billions of times per second. When you wire enough of these rapidly flipping switches together into circuits, they suddenly become capable of performing logical comparisons, mathematical additions, storing memory, and executing complex decision-making. They are the exact foundational building blocks of a functioning computer processor. Now, while having small individual transistors was totally amazing, the late 1950s brought the next massive leap forward. Two engineers, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor, were working completely independently, and they actually both made the exact same groundbreaking discovery. They figured out, hey, instead of painfully wiring individual transistors together by hand, one at a time, what if we could manufacture entire circuits directly onto a single tiny chip of silicon? This brilliant idea became known as the integrated circuit. It meant manufacturing could finally be scaled up dramatically using precise, highly repeatable processes. The speed of evolution from this point forward is just absolutely breathtaking. We go from the very first hand-built transistor in 1947 directly to the integrated circuit in the late 1950s. Suddenly, the race is on. Engineers are just scrambling to fit more and more of these switches onto smaller and smaller chips. By 1965, we get Moore's Law, and by the early 1970s, the entire world of computing changes forever with the invention of the very first microprocessor. It's crazy to think about, but in just a few short decades, we went from a giant room full of glass tubes to a tiny sliver of silicon. And this brilliantly illustrates the relentless engine behind this explosive timeline of innovation, which is Moore's Law. In 1965, Gordon Moore, who, fun fact, would later go on to co-found Intel, made a really simple but profound observation. He noticed that the number of transistors that could be packed onto a single chip was roughly doubling every couple of years, all while the cost of producing them just kept falling. Now, this wasn't some strict law of physics, but rather a relentless industry rhythm. It was the quiet, invisible driving force that pushed computing power absolutely through the roof throughout the 20th century. To truly grasp the impact of Moore's Law, you really have to consider the sheer numbers. When that first commercial microprocessor was created back in the early 1970s, engineers managed to fit an impressive 2,300 transistors onto it. At the time, that was an absolute marvel. But compare that to a modern computer chip today. A single modern chip contains tens of billions of transistors. Just think about that density for a second. Modern transistors are packed together with such awe-inspiring precision that each individual switch is quite literally smaller than a virus. It's a level of microscopic engineering that would have seemed like absolute science fiction to that original Bell Labs team. So, why does all this microscopic shrinking matter to you and me? Well, because miniaturization is exactly what made technology affordable and totally ubiquitous in our daily lives. As the transistors shrank, the bulky household radio became the portable pocket radio. Then we saw personal computers enter our homes in the 1970s and 80s. The 90s totally untethered us with mobile phones, and the 2000s literally put the entire internet right into our hands with smartphones. Every single one of these revolutionary leaps forward was made possible entirely by the transistor becoming smaller, faster, and cheaper. Yet despite all of this amazing progress, from a giant, sweltering room in 1945 to a sleek device in your pocket today, the core theme remains beautifully unchanged. Every single time your device loads a video, processes a tap on the screen, or calculates a route, it is doing so using the exact same fundamental mechanism discovered in 1947, a tiny signal controlling a much larger one, opening and closing a gate for electricity, on or off, 1 or 0. The mechanism itself hasn't changed at all. We've just learned how to paint it on an unimaginably small canvas. And I really want to hit you with this number just one more time to really let the staggering scale of this sink in. Tens of billions. Next time you look at a tiny sliver of a modern computer chip, remember that you're looking at a bustling, microscopic metropolis. Tens of billions of distinct, perfectly working parts etched completely invisibly into silicon, all coordinated by software to perform calculations at speeds that honestly completely defy human comprehension. So, as we wrap up today's explainer, I want to leave you with one final, totally mind-bending thought to take away with you. Take a look at the device you're using to watch this right now. Just look at it. Beneath the smooth glass and the sleek metal casing, how many invisible, virus-sized switches do you think are flipping precisely, flawlessly, billions of times this very second, just to bring my voice to your ears? It's hidden, it's microscopic, and it is a truly incredible feat of human ingenuity. Thank you so much for learning with me today, and hey, keep wondering about the hidden world right in front of you.